All right. Now we will consider this polarization. So 7.2. So again, we go back to this epsilon sub 1, epsilon sub 2 coordinate system. Now we'll consider one wave. Then we define the polarization as the vector magnitude of the electric field. So this electric field. Now in Jackson's now in this section 2, the notation is a little bit different. So the electric field has these two components along the epsilon 1 and epsilon 2. Right. Generally, you can have both of them, right? Both along both directions. So E sub 1 vector is this use this epsilon 1 vector and E sub 1. Now this is a scalar, just the magnitude. This is the direction, and then you have this phase vector e to the I. Let's now use a wave vector. So it's not very consistent. Anyway, K is just basically K is just like what we did with K. As you go back to the old definition, it's just the same. Okay, and then E sub 2 is obviously following the same kind of definition. So you separate the wave in two components. One is along epsilon sub 1, the other is along epsilon sub 2. Now, generally, it is magnitude E sub 1 and E sub 2. They can be complex. The more complicated situation, of course, when they are complex. But now the easiest easiest situation is when, although they may be compact, but if they have the same phase, it means you can say epsilon 1 divided by epsilon 2 is a constant. It's a real number, or you can say they have the same phase, whatever the phase you call it, by E sub 2 will have the same. If these magnitudes satisfy this relationship, the same complex phase, same dependency on exponential part of the complex number, then that is a situation of a linear polarization. Okay, so basically that you can now combine the two into here. So E will be, so the E will be just like combine everything. You have epsilon 1 magnitude of E1, and then epsilon 2 magnitude of E2, and then the exponential function e dot x minus omega t plus 5. Okay, so all the complex thing is in this exponential function, but the directional thing is all real. This is real. This vector is like you represent this a combination of epsilon 1 and epsilon 2, so it's actually a new vector. And this will be your whatever the magnitude, or ips. So you call this ips. Script E vector. So that's the amplitude of the vector field. So that's you can call that the polarization. And so this E sub 1 is the polarization of this component E1. E sub 2 is the polarization. I mean, E sub 1 times E epsilon 1, E sub 2 times E epsilon sub 2. These are the polarization of the individual component. But if you have the waves as combination of these two components, then the combined polarization is this script E is this add up this one with if they are of the same phase. And because this is real, so this just means that the wave, at least the electric field, is oscillating back and forth along this direction. It's constant. It doesn't vary as you propagate. It's always the same. As you propagate, you only change this omega t. So just a sinusoid to in. So you fix x. So fix a location x. You see this wave just oscillating along this. You always observe the wave linearly changing this electric field direction. And likewise, obviously, the magnetic field will also be linear. The magnitude is also, or the amplitude is also a constant direction because B is n cos E, n cos E. So if this is linear, then the magnetic field is also linearly oscillating. Okay, but we usually define the magnetization, not the polarization, using the electric field magnitude rather than electric field amplitude rather than magnetic field. That's just the way you call it. Okay, and so it's okay. So that one is the easiest one. It's okay, linear polarization. So that should be straightforward. Now the complication is now the elliptic polarization, but for a special case of elliptic polarization, it's a circular polarization. So we'll talk about circular polarization first. Now the circular polarization is that they are not satisfying that, but then they have a 90-degree difference, or you can say this is plus I. However, 2, or you can say this exponential function is just I. There's an I here, or I or minus I, doesn't matter. Right. In this case, then you have this you have the I here. Now this is not real, and the polarization will change in time or change in space. If you fix a space, then they will change in time. You fix a time, you change in space, right? And that's the elliptic polarization. In generally, if it's the magnitude E sub 1, E sub 2 are not the same. This generally is elliptical. But for the circular polarization, if they are the same, if E sub 1, E sub 2 are equals to the same constant, then that would be, this is for circular polarization, you have these epsilon sub 1 plus I, epsilon sub 2 or plus or minus, and then you have E sub 0. That's the magnitude of both of them are the same. Okay, you can actually have a negative sign. Okay, so that is 7.20. And we have time to figure out how it rotate in time. So we'll probably need to wait until next time. So it's a complex direction, but what does it mean? We'll need to go back to real space to see how it changes in time for a fixed space, or vice versa for a fixed time. What is changed with x? And we'll consider that later. Right? That is we'll see that is rotate one way or the other.